Okay, so we're going to continue this afternoon's session with Paola Cappellaro, who's going to be telling us about quantum control. I certainly look forward to this.
Okay. So does, yes, this work? A bit high. Okay. Thank you very much. And I'd like first to thank the organizer for giving me the opportunity to present some of my work here, and especially for putting together this session and making my life a bit easier. So I'm the third Italian speaker now. So Ben, I are used to the accent, so you will have no problem in understanding me. So the second thing that I want to do is also to thank all the people in my group who are actually the people doing the job. And if you are interested more in what we do and maybe even interested in joining us, I have a postdoc position, so look us up in online at cac.mit.edu. So what we do in my lab is using condensed matter systems to actually sort of probe atomic-like systems. So we are sort of at the interface between atomic physics and solid-state systems, and also the interface between physics and engineering. So we would like to build, if you want, quantum devices using these special atom-like systems. And in particular, the system that we use the most is the nitrogen vacancy center in Diamond. So it has become a very, very popular system. So I've been able to condense down my 4 or 5 slides of introduction about the system into a single one. And I can probably also skip it unless somebody has a question and has never seen. I want at least to point out something. So it is, if you want, the nature trapped molecular ion. And we like it a lot because it has very good coherence properties. But it has very good coherence property if we do something to it, if we control it. As it comes, it will not have such good coherence properties. And this makes what we do for any other application, from quantum information to quantum sensing, it sort of makes our life a bit more difficult, but also, if you want, more fun. So one of the things that this system is very good for is to detect magnetic field. And this was, if you want, the first proposal on how to use NV center as quantum sensors. And the idea is that we really achieve very good control on our system. And naturally, because it's in the solid state, it has very good localization. So we can achieve very high sensitivity and combine with very good spatial resolution. And the principle is very, very simple. So you will have some Zeeman interaction with an external magnetic field. You can use, for example, a typical Ramsey type sequence in which you will detect some phase due to the precession of your spin in the magnetic field. And of course, the advantage is that you can bring your system very close to the source of the magnetic field. And this was a cartoonish picture that I had back in 2008 to show how we could actually do that. So you bring your nanodiamond close to the source of the magnetic field, for example, some nuclear spin. But this cartoonish picture has actually been made a reality soon afterwards. So this is an AFM tip to which is attached a little diamond slab with a diamond pillar which contains one of these NV centers. And so we really have the possibility to use this type of system to detect magnetic field with this combination of sensitivity and spatial resolution, but it's not the only advantage. There are 2 other main advantages, which are, first of all, we can operate at room temperature. That makes my life easier. I don't need to use cryogenics. But it's also very important when you want to talk about some practical application of these quantum sensors. The other thing is that, of course, it's diamond, so it's just carbon. It's very highly biocompatible. You can put your nanodiamond inside cells, and apparently this advanced automatically. I don't know why. You can put it inside cells, and so the cells keep living without any problems. And fundamentally, what we do is actually to just measure frequency shifts. So anything which causes a shift in our diamond resonance line can be sensed. So people have come up with the idea to measure electric field, temperature, pressure, strain, rotation. If you can think of something else, let me know, and I'll try to measure it. I'm sort of short of on ideas right now. Of course, there are also various schemes with which we can measure. But again, we come back to this idea that we really reach these very good properties by applying some control. And so this is sort of the rule of the game that we try to play, because to reach very good sensitivity or reduce the error as much as possible, you would like to have long interrogation times here, tau. But of course, this interrogation time is limited fundamentally by the coherence time of your qubit sensor itself, and also maybe less fundamentally, but also very important in practice, by time variation of your source of magnetic field or electric field, temperature, and so on and so forth. We might also have some problem with the bandwidth. If you have a phase wrap up, you do not know if you're measuring a 2 pi plus pi over 100 or just pi over 100. And we need then some tools to try to solve this problem. And what I'm saying, I do not know what I did. OK. What I'm saying is that you should keep calm and use quantum control. And hopefully, you will manage to solve these problems. And hopefully, I'm better at controlling quantum systems with this remote. Otherwise, I'm So what can we do to control quantum systems? People have been controlling quantum systems for a long time in various applications. And most recently, for the goals of quantum information, there has been a lot of advancement in the techniques for controlling systems. Now, what I'd like to do is instead control a quantum system with the goal of using it as a quantum sensor. So I have maybe some less stringent requirement. I do not need, for example, universal control. On the other side, I also have some new challenges, because there is always a compromise between how much I'm trying to decouple my system from the environment, and instead how well I can keep it connected to whatever field I'd like to measure. So to illustrate this compromise, we can just consider the simplest possible control sequence that we might want to apply in order to refocus noise effects. And this is just a spin echo. So if we apply a pi pulse midway the evolution of our system, this will refocus any quasi-static dephasing noise. And so we will be able to prolong the coherence time of my system. Of course, if I'm trying to measure a static magnetic field, for example, that's also canceled out. So I do not have any noise anymore, but also I have no signal anymore, which is not really good. So what can we instead measure? Well, if I have an oscillating magnetic field, now the phase acquired in the 2 halves of my evolution adds up constructively, and so I can, again, measure the strength. So this sort of indicates that there will always be a compromise between how much signal I can get out of my time evolution and how much I can reduce the effects of the noise. So here I was applying just 1 pi pulse. If I want to increase my coherence time, I can apply, for example, 2 pi pulses or 4. And this will refocus the noise better because I can cancel out also some time-varying magnetic field. What I can do then is to look at what is the sensitivity of the quantum sensor. In principle, it should improve as 1 of square root of the interrogation time here. But as soon as I reach the limit of my coherence time, T2, now I have some exponential increase of the sensitivity or the error in the measurement itself. So what I can do is to increase even more the number of pulses. This shift my coherence time allows me to go to a slightly better sensitivity. I can do even more pulses. But of course now, the signal that I want to measure, the field that I want to measure, needs to oscillate much, much faster. So what I'm changing here is not only the sensitivity, but also the frequency of the field to which I'm sensitive to. And here I'm sort of labeling this with the usual color code for frequency. In this case, these are megahertz frequency. And I can map out all possible sensitivity for all possible frequencies. And I can do that for this type of pulse decoupling, which I'm doing some pi pulses, or I can also use some different type of decoupling, for example, some continuous drive of my system. So from this type of picture, what we learned were actually 2 lessons. So first of all, by doing this type of experiment, we do not only learn about the strength of the magnetic field that we are measuring, but also something about its frequency component, about its dynamics. And the second thing is that if I do some more generalized dynamical decoupling scheme, maybe I can do also something different, because there are differences between these 2 maps if I do some standard decoupling or some modified decoupling. So there is some more variety of things that I can do to control my system and maybe learn even more. So what we did was to apply these 2 lessons to 2 possible applications. So one application was in trying to actually learn about the dynamics of magnetic field. And another application was to try to really use this fact that we are sensitive, in particular to particular frequency, to do spectroscopy on an ensemble of nuclear spins. So with respect to the first application, what we wanted to do was, instead of just parameter estimation, as is done usually, we wanted to do time-dependent parameter estimation. And we wanted actually to achieve many different wishes, if you want, about how to go ahead and do this in an efficient way. So we wanted to have long interrogation time so that we were able to have high sensitivity. But in order to achieve this long interrogation time, of course, we need long coherence times. So we wanted to be able to apply some type of decoupling without canceling out the signal that we were trying to measure. And at the same time, just for simplicity, we wanted to have some efficient encoding of this time dependence on the phase, which is what we are actually measuring, and also being able to implement it experimentally in our lab. So what we came up with was to use a complete basis onto which we sort of project out this time dependence of the magnetic field. And in order to make it easily implementable in our lab, we use a digital set of functions, which we can actually just implement by applying pi pulses at the times where which this function, this wash function, switch sign between plus or minus 1. If we modulate in this way our system, the phase that our qubit sensor acquires is now weighted by this function itself. And so the phase is directly the basis coefficient of this particular wash function. Using this idea, this time it wasn't me. Thank you. Using this idea, we were able to measure arbitrary time-dependent functions. So we collect the basis coefficient for, in this case, 32 basis functions. And then we use that to reconstruct the time dependence. And in this case, just for demonstration purposes, we simulated with our microwave strip line the signal which would have come out of a neuron during an action potential. So it's just some weird shape, but we are able to reconstruct it with very high precision. The second type of application which I want to discuss today, is instead in trying to do NMR spectroscopy, but now down at the atomic level, and so using the MV center again to detect the structure of molecules or proteins. So the idea is that if we have an MV which is very close to the surface of our diamond's lab, it might be able to sense individual nuclear spins. So the sensitivity and the coherence property of the MV centers are such that it might be possible to really sense individual nuclear spin. And this should be quite interesting because that allows us to use just a single molecule and being able to reconstruct its structure. And this is important because there are a lot of biomolecules or proteins which cannot be synthesized in large volumes or which cannot be detected by usual methods such as X-ray crystallography because, for example, they cannot be crystallized. For example, membrane proteins are very important for drug development, but it's very difficult to make crystal out of them, especially large crystals. So the idea is to instead use this novel quantum sensor and use its coupling to the nuclear spin to detect the structure of the protein itself. And there are various groups working on this. with different methods, and probably on Monday you've already heard something about this. What we would like to use is, in particular, the leakage of polarization from the NV center, which can be polarized optically, to the nuclear spin. And the two can be put in contact, energy contact, by sort of driving the NV center at the resonance frequency of the nuclear spin themselves. What is nice is that the NV itself creates a magnetic field, which sort of changes the resonance frequency of the nuclear spin which are close by. So we can use the NV center for two different effects. So first one is, of course, to use it as a sensor, but the second one is to use it as the source of a magnetic field which will differentiate the nuclear spin themselves. And then we really sort of try to exploit the fact that we are actually using a quantum sensor, and this quantum sensor also has a small ancilla close by to it. It's the nuclear spin associated with the nitrogen spin, and we can use this in order to achieve a much longer time memory and the quantum error correction protocol to enhance the coherence times of the NV center itself. So as I said, the sensitivity of NV center is such that it is possible now to detect single nuclear spin. And this has been done with very sparse nuclear spin systems, in particular inside the diamond. We have carbon-13, their spin 1/2, and it's possible to detect individual spins. The problem is that if I want to apply the same type of method to detect, for example, spin in a protein, the density of the spin is so large, which even if I were able to detect a single spin, now I do not know which spin it is. I will just see the signal coming from all the spin in the protein. So the problem is no longer or not only to increase the sensitivity of the NV center sensor, but also its frequency or spatial resolution. So how can we do that? Well, for example, the first thing that you could do is to say I have two nuclear spins which are nearby, their frequencies are very, very close. But of course, we could try to add a magnetic field gradient, and this will shift the two energy. Now they're shifted, the two nuclear spins have a slightly different energy resonance frequency. And as I said, my NV sensor, by using this decoupling technique, is very sensitive to different frequencies. So maybe I would be able to measure this resonance frequency. However, this gradient might not be strong enough. These are nuclear spins, so they do not couple very strongly to magnetic field. So what we can do is to try something else and introduce some extra control on our system in order to try to cancel out completely the coupling to one of the two spins. So what we can do is to alternate evolution under the gradient created, for example, by the NV spin or by some external magnetic tip, and evolution during which we put in thermal contact the spin, the NV spin and the nuclear spin. And these two interleaved evolution create a frequency comb which will allow us to retain only the coupling to one spin and cancel the coupling to the other one. And this allows us to have much better spatial resolution. So the pulse sequence looks something like this, and this becomes more and more complicated as soon as you start adding things. So we put this period of time during which we have this polarization exchange between the NV and the nuclear spin, and we alternate it with evolution under a gradient while we sort of preserve the coherence of the NV sensor onto the ancilla of the nuclear spin associated with the NV center. And by repeating these two steps, we create this frequency filter which cancel out coupling which are not to the correct or the desired spin. So what we can do then is to try out this type of sequence, at least first with simulation, and then right now also with experiment, but unfortunately I can only show simulation for now. And we just took some typical protein, and what you can hope to measure is some portion of the protein itself at the surface of the protein. But this might be some important part of the protein because it's the one which is responsible, for example, for attaching to drugs or other ligands. And so what we can do is to follow the polarization leakage from the MV to different resonance nuclear spins. And again, because of this filtering action on the gradient, we can have very sharp frequency resolution of our spectrum, and we can really detect that here we had 9 spin. There were actually 11 of them, but some are sort of overlapping. This is still not enough to actually resolve the complete structure, because what we have is a symmetry overlap of these 2 spins. So these 2 parameters, the dipolar coupling between the NV spin to the nuclear spin, sort of have this intrinsic symmetry, and so we cannot know where on these cones the spins are. What we can do is to rely on the coupling between the 2 in order to break this symmetry and actually acquire all the structure of the system. So I'm out of time, but the idea is to sort of inject polarization into the nuclear spin system, let it evolve for some time, and then measure it back. And this will reveal 2D type of spectra in which these peaks at the sort of off-diagonal peaks reveal correlation among the spin, which allow us to detect coupling among the nuclear spin themselves and reconstruct the structure. So with this, we'll conclude. And just want to say that using quantum control to manipulate a quantum spin sensor is really the way to sort of achieve a more efficient way of extracting information from very complex systems, be them varying in time or in space, like this nuclear spin system. Thank you very much.
Do we have any questions for the speaker? So, same rules apply, Bill. So I have a question. So I'm really interested in this this technique of using a complete set of digital states to extract information. But I guess my question is, each one of those is also sensitive to noise and certain bandwidth. So to what extent do you have better noise performance with that than other techniques?
So, so each one of these wash sequences have sort of similar noise performance with respect to all the other ones in the same order of the wash sequence, if you want. Like the cancellation of the noise is sort of similar up to a certain order. So you should not be skewed too much in terms of how much noise cancellation you have in the reconstruction process. On the flip side, if you know that if you, for example, know already what is the time dependence of the field that you want to measure, then you could use your knowledge of the noise spectrum and of the field that you want to measure to pick which one of these sequences is the best one, the optimal one, to detect that particular time dependence. And so, I mean, there is like some sort of a modulation of how much strong the noise is going to be, and you can exploit that, but in general, it should not be like too much of a problem for general reconstruction.
So the sensitivity is off. Right. So the sensitivity that allows you to see singular nuclear spins is just amazing. If I'm remembering correctly, earlier in this meeting, we were told that at some distance, I forget what it was, maybe 10 nanometers, you could see single electron spins. Now, of course, you've gone to a distance of -2 nanometers, but I get the feeling that that's not the only reason why this polarization transfer seems like a key thing. And the fact is, I didn't really understand it that well. So could you tell us a little bit more about that? And so, is this a key to getting this extra sensitivity?
The key is to just get closer. But as you say, you cannot go to -2. But like when you go to about like 2 nanometers from the surface, then you get into business of sensing nuclear spins. So people have already sensed a small ensemble of nuclear spin down maybe to the like 10 nuclear spin, more or less. So, and the other key issue is getting closer, but also maintaining the coherence property.
Yeah, so the quantum control
exactly.
things, the dynamic decoupling was important.
And that is given by quantum control, but also by having better materials property like surface properties. So this polarization leakage, basically what you're doing is you're continuously driving the NV center. And so that decouples the ambient center from noise. And it is slightly, I mean, it's on the same order, but slightly better than doing pipe pulses, if you want. And at the same time, you drive at a resonance, like the Rabi driving should be matching the resonance frequency of the nuclear spin. So in this way, if you want, in the dress basis, the NV has the same energy as the nuclear spin, and so they can sort of flip-flop without changing the energy, and so you can transfer polarization to the nuclear spin. So this is the principle of how it works.
Could I think of the continuous decoupling as being something like a Zeno effect?
So some people say that any form of decoupling is the same as Zeno. You can rephrase everything in the same framework if you want. So even like the post decoupling, you can consider it some kind of Zeno effect. I do not know. I mean, it's a border-like definition, and